Hello, everybody. Let's take a look at the exam for this year. So we've got our exam. Let's see what we're going to define the settling time and overshoot. Settling time. It takes to move the system to within 2% of the steady state. So you can talk about unit step, different things if you want. Final value, that kind of thing. Percent overshoot. Percent overshoot. The amount the system extends past the steady state during a step. Percent overshoot. Max minus steady state times 100. List 4 reasons to use automatic error feedback in the system. Okay. Okay, 1, reduce the steady state error. Change, hopefully improve, the dynamic response. Reduce the effects of disturbances. Reduce the effects of parameter errors. Give an example of open loop control and closed loop control. I've talked about this several times. Garage door. I put it, there's a number of different things. People talked about cruise control. I don't know if this is emblematic of this class or not, but there was in this one, there was a lot. Coffee grinders. I don't know if that's a new thing in the book. Cruise control, I talked about even the biological temperature control. Also thermostat. You know, there were a number of different issues here. Describe 2 ways of obtaining the root locus. Now, there were a couple of different people who also answered this a little differently, and I was just fine. By hand, I said. You can obtain it by hand. You look at the start and end points, asymptotes, real axis segments, etc. You could, or 2. So a lot of people did this and described some of these things. 2, I was wanting you to say it like MATLAB. Hey, just ask MATLAB. R locus. And then, another one that I didn't really think of at the time, but you could just buy it from a colleague. I don't know. There were other ones. What assumptions must be made to define the system transfer function? Okay, so must be initial conditions have to be equal to 0. That's the most important one. There were other things. It has to be a linear system. It has to be single input, single output. There were a number of different things. Those are also things you can do. All right, so how would we grade this one? Here's how I would grade it. So each one of these is worth 5 points. So you automatically get 1 point here. 2 points for each one of these. You had to have a little bit of something more along these lines to move the system within 2% of the steady state. You had to have it that it goes past the steady state. If you had the formula in here, that would be good. And this one, you get +1, 1 for each one, +1 and 4 for each one. So, I mean, I told you this was going to be on the exam. These are the reasons. These are important. Each one of these reasons is important for when you're trying to control something, to think about why the closed loop control improves these issues. Give an example of control system. So again, here you just get 1 to start with and 2 each for either one of those descriptions. Describe the root locus. Again, you get +1 just for anything, and then 2 points for each of the 2 ways that you decided. And then here, this one, you get you would just get plus 1 to start with, and then, again, two. Really, this one is the most important one, but then for anything else that you write, what you would get 2. So that would be 25. So that's how I distribute the points. Okay. All right. Given the open loop control system with m equals 5, design a controller for the system. Design a controller for the system. 1, show the control structure. Okay, did somebody say the word control? Because I know what control means. It means that you take the control variable, you multiply it by some gain times the desired minus the actual. That's the control structure. When I say show the control structure, what I really want you to do is I really want you to show me the control structure in a block diagram. Something like that. So that's really what I wanted you to get to here. Now, I'm going to go ahead and say, hey, here's a loop here, and I'm going to use the formula to figure out that this loop, the equivalent of what's inside this loop is 1 over ms. And then just, you don't have to do this, but, keep things a little cleaner. However I can do it to keep things clean, 1 over ms plus b, 1 over s. So I don't mind. I love drawing block diagrams, so I just keep drawing them over and over again. Plus, minus. Even if I was using Simulink, I would make sure that I would first do the block diagram this way, and then I'd make sure that the system output is the same for this block diagram. Theoretically, it should be, so we should do. And then in this case, I can say that GH of S is equal to KP over ms squared plus bs, which, again, maybe what I'm going to do is get that m out of here and then b over m. Maybe I'll do that just to clean up things algebraically in terms of it. Again, sketch the root locus for b equals 10, 40, and 60. So what I can see here when I do this is I can see that I've got one pole at the origin, at where s equals 0, and I've got one pole at a equals b over m. And so b over m in this case is going to be, so let's make a little table. Here's b is going to be 10, 40, and 60. And then I'm going to look at what the root is. The second root is going to be 10 over 5 is 2, and then 40 over 5 is 8, and 60 over 5 is 12. So 1, 2. So here's the root locus here. So I can just immediately kind of figure out the number of asymptotes is 2. It's the sum of the number of poles minus the number of real zeros. There's just 2. The angle of the asymptotes is 90 degrees, plus or minus 90 degrees. And so we can look at where the sigma asymptotes is the sum of the poles minus the sum of the zeros. In this case, it's just 1, or it's really just b a over 2 is where it is. It's in this, for second order systems, that's pretty standard. And so I can draw this root locus this way, and I will know that it goes up this way and it goes down this way. So there's for b equals 10, and so when b equals 40, then it's going to be s equals 8. So that's 5, 6, 7, 8. S equals minus 8. And again, it's going to be the roots. All of these things still apply. And now what we're looking at is that the asymptotes are at plus or minus, at 90 degree asymptotes at plus or minus 4. Sigma A equals minus 4. And then again for b equals 12, 10, 11, 12. Hey, look at that. I gave you the right number. I can also look at these asymptotes that are going to be at sigma A equals 6. So here's the root locus for all three of those things. Oh, I should have mentioned here, real axis segments for this one. I should put those in. And just kind of, make sure I do those. I kind of skipped that step. Okay, so I sketched the root locus. That's number 2. For each value of b, show where on the root locus you'd like to place the roots to give zeta equals 5%. So 5% is about 45 degrees. Do I need to get out my protractor for this? No, I can kind of estimate 45 degrees. So I can put my desired root locations here. Desired root locations there. Show the closed loop transfer function. Show the closed loop transfer function. So I can go up here and look at what the closed loop transfer function T of S is going to be theta over theta desired, which is going to be the numerator of G times the denominator of H divided by the denominator of G times the denominator of H. So it looks like that. If I want to, I could reformulate this just a little bit, Kp over M divided by S squared plus B over MS plus Kp over M. And then what we see here is that, again, in nomenclature terms, we can S squared plus 2 zeta omega NS plus omega N squared. So we can do all that. Determine the settling. So I realized I kind of swapped these. I should have asked the first one. Determine the value of K for the closed loop unity feedback system when B equals 30. Well, this says determine the settling time in each case. So the settling time happens right here at where sigma A is equal to minus 1. And so maybe I want to figure out again, here's zeta omega n, in this case is 1, 4, and 6, and that means 4 over zeta omega n is going to be 4 seconds, 1 second, and 2/3 of a second. So maybe I want to put the settling time here, TS. Maybe I want to do that. And then it says, determine the value of K for the closed loop unity feedback system when B equals 40. Okay, so if I want to find out what Kp is, I'm just going to look at what the magnitude of 1 over GH is, and that's going to be the magnitude of S plus root 1, S plus root 2. Sorry, I messed up here. I got involved in this. Let's get rid of that. S equals minus 8. And then this is what's going to be on the bottom of this, in this case, is Kp over M. So that's the numerator of the numerator. So I've chosen to use the canonical form because then I can just write these things. And then what I really have to do is draw the vector, where this is the vector S plus R2, and this is the vector S plus R1. And then if I want to measure the length of those things, like I could just get myself a scrap of paper. I mean, I can figure this stuff out analytically if I want to, but that's like more trouble than it's worth at this point in time. I'm just going to get a scrap of paper and grab it on here and say, okay, let's see. So that's, what have I got? 5. So that's 5.6. 5.6, 5.6. K over M is, oh, sorry, this is not Kp, this is just 1 over M. Kp's on this side. I solved this equation, T of S, for Kp. Just so you know, I just made an algebraic error, so it's 5.6 over M, so it's 5 times 5. And this is 1 over M, so it's 5 times 5 is 25, times 5 is another 125. So that's about, Kp is about 125. It's just rough estimates, right? So there we go. All right, so now, how do I grade this thing? So if it says, for part 1, 2, 3, 4, 5, 6. So there's 6, 1, 2. So I give you 5 points for showing me the structure. I'm going to give you 4 points for showing the root locus, and 3 points for showing me where the desired roots are. And then I'm going to give you 4 points to find out what the transfer function is, 5 points for the proportional gain to find the gain value of whatever, so however much of this you got right, maybe you lost a point or two, something along those lines. And then I also give you another 4 points for telling me what the settling time in each case is. All right, for each pole zero plot of the open loop system, sketch the root locus and write the transfer function for the open loop system. Helpful hint, there is a time limit and complete accuracy is not expected. So, what I didn't want you to do is find the exact breakaway and breakout points for each one of these things. So what we have to remember is that the root locus starts at the poles and ends at the zeros. You just kind of have to figure out how that works. So, if we're going to start it, so where are the real axis segments? Real axis segment here. How many real axis segments? Real axis segments is the number of the poles minus number of zeros. There's no asymptotes. So there's no infinite asymptotes on this one. And so what that means is this thing breaks away somewhere. And I don't even care how you drew this thing, but somehow it does something like this. Like if you want to draw it this way, I don't mind if you draw it this way. I probably would object a little bit if you draw it, maybe this guy's been drinking a little bit or whatever. I don't know. That would have been, I would have counted that, I can tell you. Just it has to start at poles and ends at the zeros. Okay, so what are the roots? So what does this transfer function look like? G looks like something like this. So we have to look at what the poles are. So this is a 2 minus 2. Let's see, 1, 2, 3, 4, 5, 6, and minus 6. So this is S plus 2, S plus 6. This one's a little harder. So this one is 2. This is plus 2 plus or minus 3i. Some people even wrote it this way, and I'm going to write it this way too. I certainly don't mean for you to multiply out 2 plus 3i and 2 minus 3i. I don't want you to convolve that statement. So people just wrote it this way. I would write it this way: plus S plus 2 minus 3i S plus 2. Oh, that's a minus sign there. Sorry. Minus 2 plus 3i. So I'd write it that way. I was pretty liberal on these transfer functions, so if you want to try and worry about that, that's all right. In the end, maybe this hurt you, maybe it didn't, but in the end, the way I'm going to grade all these, just so you know, just right from the start, the way I'm going to grade it is I'm going to give you 5 points for the transfer function. Overall, and then 4 points for each one of these things depending on how you did it, because you've got the real axis segments, you've got the infinite asymptotes, you've got the start and end points, and then maybe a point other than that. Okay, so here's 1, 2, 3, 4, 5, 6. So here's the real axis segments for that thing. They start at the open loop poles and ends at the open loop zeros. So I'm just going to say somehow this has to break in here and go this way and that way. And then if I look at what the transfer function is, g of s is equal to, so I'm just going to draw a line here. This is going to be 5. So 5, 10, 15, 20. So that's going to be s times s squared, s plus 20. And then this pole is 5, s plus 7.5. And this is 5. It's like 5, 10. I think I would have shifted these if I'd have known I was doing that. 12. S plus 12.5. I would have probably shifted those. So again, how many infinite? On this one, there's no real axis segments. There's no real axis segments. There's no infinite asymptotes. And so again, I'm just going to say these things go in this way somehow. We should go over a little. We haven't gone over some of the details, but in general, that's what we of exactly what angle does it break away, what angle does it arrive. We can look at those and talk about those a little bit more. So G of S, again, this is going to be 100, 200, this is 300 I, and this is 100, 200. So this is going to have roots that are going to be S plus 200 minus 300 I, and then this is S plus 200 plus 300 I. So that's going to be S plus and minus 200I. And then what goes on the top is just S squared. Is there a constant involved there? There could be. You could put, oh, I should put a constant in there too, because I can't really tell anything about the constants here. That's fine. I don't mind those. Okay, again, so here we are, real axis segments, 0, 0, 0, 1, 0, 1. How many real axis, how many asymptotes? Just one. Here's the asymptote going off in this direction. And then what we would do is we would know that these things have to come in and hit the real axis in some way. One of them goes towards the zero and one of the finite zero, and one of them goes towards the infinite zero. Again, this is going to be minus 2. So this is 1, 2, I. So this is going to be G is equal to so it's going to be, so this is going to 2, this is minus 4. So let's go S plus 4. That's what's on the numerator, and what's on the denominator is going to be S plus 2 minus 2I, and then this is S plus 2 plus 2I. And so here's final one, G of S is equal to, so we can just look at here. Let's see, this is 2, 1, 2, 4. Again, I think I shifted these, and I probably would have shifted them. This is going to be 2 minus 2.5, 2, 4. Oh, sorry, no. 1, 2, 3. Oh, I'm an idiot. Okay. 1, 2, 1. No, wait a minute. Let me count on my fingers. 1, 2. Okay. So this is 3, 4, 5 minus 5, 6, 7, 8 minus 8. So we've got zeros at S plus 8, another 0 at S plus 5. We've got a pole at S equals 0, and then another pole at 1, 2, 3, S plus 3. Real axis segments, 1, 2, 3, 4. How many infinite asymptotes? It's going to be the number of poles minus the number of zeros. So the number of infinite asymptotes is equal to 2. The angle of the asymptotes is equal to the sum of the poles minus the sum of the zeros. It's going to be 0 minus 3 plus minus, so it's a minus 5, so it's plus 5 plus 8 divided by the number of poles minus the number of zeros, which is 2. So that's 5, 8 and 5 is 13 minus 3, so it's going to be 10 over 2. I'm just making sure I'm doing my math right. 1, 2, 3, yeah. So that's going to be 10 over 2, which is 5. 1, 2, 3, 4, 5. So I have to put another line here. I didn't realize that. 1, 2, 3, 4, 5. And then I say 1, 2, 3, 4, 5. So here's my infinite asymptote. Something at sigma A equals plus 5. Notice it's plus 5. And so what I don't know is there's two ways of drawing this root locus. So one of them is to just draw the root locus so it goes up this way. Maybe these guys go to the infinite asymptotes, and maybe these guys break away and come this way. That'd be one way to draw it. There's a second way to draw this, and it could be that these two break away and move up to the infinite asymptotes. And these two come in and go towards the finite zeros. So either one of those would be fine. And again, if the way I would be drawing it, the way I'd be grading this is I'd be giving you 4 points. I'd be giving you 4 points. If you did all the things right, I give you 4 points. That's 25. Okay. We've developed dynamic equations for the motion of a satellite. Now we've done that. That system is shown in the red box. So I've shown in the red box. So as it turns out, there's a slight delay in the force supplied by the thruster. So I've included that slight delay of the thruster force in the satellite. Now, where does that delay come from? Well, maybe our motor, electric motor, you know, we know that the dynamic equations for electric motor also include a time delay between the instant that I apply the command, time t equals 0, and the time that our electric motor comes to settling at its point, we could call that some kind of a time delay. So we know there's a time delay in there. All right. And so sketch the root locus. As it turns out, there's a slight delay. Sketch the root locus for the open loop system, including the thrust delay. Okay, so the open loop system, including the thrust delay. So this is the open loop system, including the thrust delay. So there's 2 poles at the origin. It's got it's got 1 pole at s plus 10. So we kind of have to decide, like, where is 10? 1, 2, 3, 4, 5. I probably should have let you see this. 4, 6, 7, 8, 9, 10. This is all right. Maybe this is the hardest part to do. So I've got 1 pole at s plus 10. And so if I draw it, so I've got the number of asymptotes, number of infinite asymptotes is the number of poles minus number of finite poles minus number of finite zeros, so it's got 3. And that gives you, it's plus or minus 60 degrees and 180 degrees, 180. So here, and I can do real axis segment. 1, 2, no, 3, 4, yes. So here's the 180 degree infinite asymptote. There's 2 more asymptotes at plus or minus 60 degrees. I want to find out what the asymptote intercept point is. It's the sum of the poles minus the sum of the zeros over the number of poles minus the number of zeros. And then that's going to be, so the sum of the poles, that's going to be 0 minus plus 0 minus 10 over 3, or 10 thirds. So that's going to be 10 thirds is 3 and 1/3. 1, 2, 3 and 1/3. Here's sigma A equals 3.3. And so here's where sigma A is. So do I have to get my protractor out? Do I have to get a protractor out? I usually have a protractor around. I usually carry one. I don't know why I'm having a hard time finding a protractor right now, but for reasons I can't figure out, I am. Okay, I'll just draw it exactly. You know what, before I draw it, let me just say that it's a 60 degree. Here's the infinite asymptotes. Just estimate, right? This is just an estimate. It's an exam. Do I really have time to shift around? Oh, I got it pretty close anyway, right? Okay, good. All right, so here's the infinite asymptotes. And so now if I'm going to draw the root locus for this particular one, what I'm going to see is that these guys come up and they meet the infinite asymptotes. This one goes out this way, right? So sketch the root locus and comment on any issues you see. Let's see, what issues do I see? I have another story about this little picture here, if you want to know. Hey, no left plane poles available. Okay, there's my comment on that. Look, this, you can't, if you just use proportional gain alone, you're going to run into problems. So a standard approach, if you don't like the dynamics that your root locus has, we haven't talked a lot about this, but I'm telling you, and I give you the answer If you don't like the dynamics, hey, just add a 0. Why not? Just throw a 0 in there. All right, here's a 0 that somebody's put in there for me. Not clear exactly where all that comes from and that sort of thing, but I'm going to put it at -5. So here is S equals -5, a 0. And so now what we have is we have a little bit different approach here. So that with the 0, the number of asymptotes is number of poles, 3, minus the number of zeros, 1, is going to be 2. The angle asymptote intercept point is equal to the sum of poles minus sum of the zeros, so that's going to be 0 minus 0 plus minus 10 plus 5 over 2, so that's going to be 5 halves. And so here's sigma A for this one. It's going to be 5 point. Can somebody help me what 5 over 2 is? 5 over 2 is 2.5. 1, 2.5. And in this case, the asymptotes are straight up. I probably should have used a different color. Oh, Bradley. Bradley, where are you when I need you, baby? You had all sorts of good colors. In any event. All right, so what that means is this one doesn't change. This one still goes out this direction. I'll get a heavy blue one. And these two, then, they have to come up somehow and meet. And do I know how they meet? I'm gonna draw a little bit different one. It's likely I'm always a little aggressive about asymptotically approaching something. So it's I don't exactly know where they are. I'm just drawing a sketch anywhere. It's somewhere like that. So standard is add a 0, sketch the new root locus, and indicate points for the closed loop poles. So let's put closed loop poles. Well, let's say whichever one it is, like I want them to be up in here, as I'm kind of, this one's kind of telling me that I'm adding damping if I go this way. This one, I'm kind of adding a little damping. So I don't know, it's not very good. So I'm just going to fudge and say like, well, I would like it. So if I had drawn this one, I would put it here. If I had drawn this one, I would put it here. I would say those are my roots, the place for my open loop poles. Closed loop poles. That's where I want my closed loop poles to be. Okay. It doesn't really say anything about draw a sketch of the closed loop response. So what we can see is that the closed loop response, like maybe I have to measure this angle, but what I can tell you is that like here's zeta equals 0.707, so maybe this is going to be like 0.5 or 0.4 or something like that. So here's the sketch. Here's time. So let's go look, and are we going to look at something at 0.5, 0.4, maybe 0.3, maybe 0.2? However it is, it's going to have a sketch. It's going to show me that my omega n, I know my omega n is about 1, 2, 3. It's about 3.5. So 4 over omega n, this is at TS, is about 1. So let's say omega n is, I don't know, here's omega n, it's the length. 1, 2, 3, let's call it 3. 4 over zeta omega n, zeta is 0.5 over omega n, so TS is 4 over zeta omega n, which is zeta's, we don't know exactly, let's call it zeta 0.5. So let's call it 4 over 0.5 times 3, let's call it 4. And that's going to be 4 over 2 seconds. Settling time. So here's my sketch. Does it have my peak time? Maybe percent overshoot is maybe, I don't know. Let's see what percent overshoots, maybe like 10 or 20%, 10%, 20%, something like that. If you want to put some things there. So here's what the sketch of my locus looked like. And then it says show the closed loop transfer function. T of S is equal to theta over theta desired, which is going to be the numerator of G, KP, 10, 350, s plus a over numerator of g times the numerator of g times the denominator of h, which is 1, denominator of g, s squared, 2,000 s squared times s plus 10 plus 3,500 kp s plus a. And really, that's as far as you really need to go with it in an exam. You know, in a perfect world, you would just do this kp times 3,500 s plus 5, and then this would be 2,000 s cubed plus 20,000 s squared plus 3,500 kp s plus 3,500 times 5 times s. Right? Okay. So how would I grade this? So the way I'm going to grade this is I'm going to look at sketch the root locus for the open loop transfer function. So you should get 5 points if you drew this red thing here. A standard approach is to add the 0. So there's up to 7 points for getting that next part of the root locus. So you should look at the asymptotes. You should look at adding the 0, getting the asymptotes, real axis segments, kind of bending, doing a sketch of the root locus that way. And then for the transfer function, I'm going to give you 8 points. So if all you did was just draw the transfer function for this system, you would get a significant portion of it. And then for this sketch, it's another 5 points. Okay? Okay.